All right, here we have section 8.6 on counting principles. So there's a whole bunch of different ways to look at this. It really depends on what the question is. So let's just get started. We're selecting pairs of numbers at random. If we have 8 pieces of paper numbered 1 through 8 in a box, one piece of paper is drawn from the box, its number is written down, and then you return the piece of paper to the box. Then you pick a second piece of paper. Then you add the numbers together. In how many different ways can you get a sum of 12? So we have to keep in mind here that we're returning that first piece of paper to the box so we can get number repeats. So the easiest way sometimes I think is just to draw a diagram, make a list, something like that. There's not necessarily always a formula of how to do these kinds of questions. So if I'm going to get a sum of 12, I'm going to think about all the different ways, depending on what I picked the first time and what I would pick the second time, that they would add up to 12. So if I picked a 4, the first time to get a 12, I would pick an 8. And then I could flip that over as well. 8 and 4, 5 and 7, 7 and 5. And then since I can have that repeat, 6 and 6 also works. And those are the only 5 ways to get to 12 as a sum. Same kind of question, but this time we're picking the numbers at the same time. So it would be impossible for us to get that 6 and 6 option since I'm not putting that first piece of paper back. I'm picking them at the same time. So when I make my list this time, it's the exact same except I would not have that 6 and 6 option. 4, 8, 8, 4, 5, 7, 7, 5. So there are 4 ways that I could pick a sum of 12. So the fundamental counting principle. If I have 2 different events, and I know the first event occurs m1 ways and event 2 occurs m2 ways, to figure out the number of ways that the events can occur together, I would multiply m1 and m2. So how many different pairs of letters are in the English alphabet? Since the English alphabet has 26 letters, that means I have 26 options the first time and 26 options the second time, and I will multiply them according to that counting principle and get 676 pairs. Our telephone numbers have 10 digits. The first 3 are the area code, the second 7 are the local telephone number. We should know that at this point. How many different telephone numbers are possible within each area code? So we are only concerned with that last 7 digits. The local telephone number cannot begin with a 0 or 1. So in that first slot, I don't have 10 options. I don't have 10 digits worth of options. I only have 8 since it can't be a 0 or a 1. But all of the rest, I potentially have 10 different options for 0 through 9. So then when I multiply all those together, there are 8 million numbers in each area code. That's why some areas like the whole central Wisconsin, the 715 area code, northern Wisconsin, covers a big chunk of the state and we don't have any repeats. But if you look to a bigger city like Milwaukee, New York, um, you're going to have multiple area codes because they have more than 8 million phone numbers. Because we're not just thinking about 8 million people, but we're thinking about home lines, we're thinking about business lines, cell phones. So that adds up real quick, which is why there are so many area codes even within the same area. Okay, so a permutation of n different elements is ordering them. So permutation means order is important. Order matters for permutations. How many permutations are possible if we're ordering these first 6 letters together, A, B, C, D, E, and F? So I'm going to start, there is a formula for this that we'll get to in a minute, but if we Just think about it as our listing or our diagramming. Sometimes that gets us there in a more logical way. My first letter, I have 6 choices. A, B, C, D, E, and F. Once I've already used that letter, whichever one I used, I only have 5 choices remaining. Okay, so let's put this out in a 1, 2, 3, 4, 5, 6. First letter, second letter, so we're going to see that pattern. We don't have to write out everything. We see that the first letter has 6 choices, then the second has 5. It's going to keep going down as we use our letters and multiply them together because of that counting principle, and there are 720 for ordering those 6 letters. Now, hopefully this looks familiar to you, 6 times 5 times 4 times 3 times 2 times 1, because in the last section we were talking about factorials, which is exactly what this is. If we are ordering n elements, then we do n factorial, which is exactly what we did. We were ordering 6 letters, so we did 6 factorial to get there. And if this diagramming helps you, please continue to do it. But if you remember that trick, you can just do n factorial a little bit faster. But what if we're not ordering all the elements? What if we have 8 horses running in a race and we're just ordering the first 3? First place, second place, and third place. The first place option, there are 8 horses, so there are 8 horses that could win. If somebody's already winning, that means that there are only 7 options in the second place and 6 options in third place. So we multiply 8 times 7 times 6, which is 336 ways. And what we just did, without knowing that we did it, was taking n elements, taking r at a time, so we took 8 elements, 3 at a time, and we use this permutation formula just by using a list. Sometimes that list method is a little bit quicker because this formula, we didn't do that. We could. So that would have been, what we just did was 8p3, p meaning it's a permutation and order matters. It would have been 8 factorial over 8 minus 3 factorial, and we would have gotten 336. So if you can think about it this visual way, first, second, and third, and just list the options, it's a little bit faster, but you'll still get to the same place either way. Okay. Distinguishable permutations, generally we think about this as letters. If we are trying to rearrange a word with a certain number of letters, each one of these little categories would be how many of each letter occur, or how many of each object occur. So N1 is a certain letter, N2 is a certain letter, N3 is a certain letter, whereas N on top is just how many letters there are total. So that's what you do with distinguishable permutations. So like this example where we have the word banana, and we are trying to figure out how many distinguishable ways we can write the word banana. There are 6 letters in all, and a 6. And for our different categories, we have 1 B, we have 3 A's, and we have 2 N's. So those are our 3 different categories. Those are what's going to go on the bottom of our distinguishable permutations formula. 6 factorial on top, 1 factorial, 3 factorial, 2 factorial, all on bottom. If we don't want to do this the long way, just remember that there are factorial buttons. So I could do 6 factorial divided by, I'm not going to do 1 factorial, I know that's just 1. 3 factorial and 2. I didn't do the factorial on the 2 either because I know that's just 2. Simplified out, that is 60 ways. Okay. Combination is where an order is not important. So if I have the letters A, B, C, that would be the same thing as C, B, A since they have the same letters in them. But that would not have been the case if it was permutations because those are written in different orders. But for combinations, they would count to be the same since they have the same elements inside. So in how many different ways can we choose 3 letters from A, B, C, D, E, where we don't care about the order of the letters? We're just going to start this method by writing all of our options. So I'm just going to start it out, A, B, C, A, B, D, A, B, E. A, C, D, A, C, E, A, D, E. There's probably a better way to go through and do this. We're just trying to go off of our the best we can. B, C, D, B, C, E, B, D, E, and C, D, E. Now I think I have them all. Any other options that you could think of probably already are included in a different order. So I did list them all. There are 10 ways to do that. Now that cannot possibly be the only way to do that type of question because that could take an awful long time if you're not good at that type of thing. So there is a formula which should look very familiar for combinations. Combinations again mean that we don't care about the order. This is the same formula that we used for the binomial coefficients, NCR. So that's what we just did. We had 5 letters. So we did 5C3, which was 5 factorial over 5 minus 3 factorial and 3 factorial. If we did that, we would get the exact same answer as just by listing. Now, for that type of thing, I did not really enjoy the listing. I would have probably have preferred to use this formula. Okay, a couple more questions about combinations. A standard poker hand consists of 5 cards dealt from 52. So since order does not matter, once you put the cards in your hand, doesn't matter the order of the cards, you still have them in your hand in some extent. So 52, C, 5. 52 factorial over 52 minus 5 factorial, 5 factorial, which is a big number. So if you know poker, there are 2,598,960 poker hands possible. That's a lot. Now what if I have 2 different groups? I'm trying to form a 12-member team. I have 10 girls and 15 boys. So 2 different groups, girls and boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? So that 12 is actually not a number we're going to be dealing with. We're really just thinking about our 2 separate groups and how many we're wanting to pick from each one. So 10 girls, I'm choosing 5. And remember the fundamental counting principle said if I figure out how many ways to choose girls, I'm going to multiply that by how many ways to choose the boys. 15C7. 10 factorial over 10 minus 5 factorial, 5 factorial times 15 factorial, 15 minus 7 factorial, 7 factorial. Multiply everything together, we get 1,621,620 teams. It's a lot. It's a lot of teams. And our homework is listed for section 8.6 on counting principles.